Stop writing loops. Stop coding gradients by hand. It's time to build a brain. This is PyTorch, and we are going 0 to hero right now. In the next 15 minutes, you're going to understand how computers see. Not kind of actually understand it. By the end, you'll know exactly how Instagram knows it's your face. No PhD required. Let's teach a rock to see. Here's the thing. Computers are dumb at seeing. Give them a cat photo and they literally have no idea what they're looking at. To them, it's just a sea of random numbers. No meaning, no structure, nothing. But your brain? It instantly knows that's a cat. Those are ears, that's fur. You don't even try, it's automatic. How? Because your visual cortex does something magical. It detects patterns layer by layer. In 1989, a French scientist named Yann LeCun asked, "Can we teach a computer to see like the brain?" He created LeNet, the first convolutional neural network. It could read handwritten digits. Banks used it to read checks. For 20 years, nobody cared. Then in 2012, boom, Alex trained AlexNet on GPUs. It crushed ImageNet by 10%. This was the moment deep learning exploded. Every tech company suddenly cared about AI. Today, CNNs power everything. Tesla's self-driving cars, Face ID on your iPhone, medical scans detecting cancer, TikTok's face filters, all of it. Same fundamental idea that LeCun invented 35 years ago. So what is that idea? How does convolution actually work? Here's the entire concept in one sentence. Slide a small filter over the image, find patterns, stack the patterns, and vote on what you see. Let's build it from scratch. First, what even is an image to a computer? Before we code anything, let's clear something up. What is an image? To you, it's a cat photo. To a computer, it's a spreadsheet. A giant grid of numbers. That's it, numbers. Every tiny square on your screen is called a pixel. Each pixel has 3 numbers. How much red, how much green, how much blue. That's RGB. Mix them right, you get any color. 25500 is pure red. 00 is black. 255, 255 is white. Your whole screen is just millions of these triplets. In PyTorch, we stack these color layers into a tensor. The shape is CHW channels first. That's the 3 color layers. Then height, how many rows. Then width, how many columns. A 224 by 224 image with RGB has shape 3, 224. That's 150,528 numbers, representing one cat. Why 224? It's just a convention. Early networks like AlexNet and VGG used it. Bigger images need more compute. 224 is enough detail without melting your GPU. You could use 256, 512, whatever, but 224 became the standard. Now, how does a computer find patterns? It doesn't look at the whole image at once. That's way too much. Imagine shining a tiny flashlight over a dark painting. You slide it around slowly, and wherever something interesting appears, an edge, a texture, you mark it. That flashlight is called a kernel, also called a filter. It's a tiny grid of numbers, usually 3 by 3, 9 numbers. The kernel slides over the image pixel by pixel. At each position, it multiplies its numbers with the pixels underneath, adds them all up, and writes one number to a new map. That new map is called a feature map. Here's where it gets cool. If the kernel is designed to find vertical lines, it will output big numbers, only when it's sitting on a vertical edge. Horizontal kernels find horizontal edges. Diagonal kernels find diagonal lines. This is edge detection, and it's the very first thing every vision model learns to do. We don't just use one kernel. We use 16, 32, even 512 different kernels at once. Each one learns to detect different features, edges, corners, textures, color gradients. The output isn't one image anymore. It's a whole stack of feature maps. Each map highlights a different pattern. Let's read the code. NN do, parentheses, 3, 16, kernel size equals 3. The 3 is input channels, your RGB. The 16 is output channels. We're using 16 different filters. Kernel size equals 3 means each filter is 3 by 3 pixels. PyTorch learns these filter values automatically during training. You don't hand design them. 1. Gotcha. After a 3 by 3 convolution on a 224 by 224 image, the output is 222 by 222. We lose 1 pixel on each edge because the kernel can't center on the very corner. To keep the same size, we add padding equals 1. That pads zeros around the image, and now output stays 224 by 224. After convolution, we have 16 feature maps, each 224 by 224. That's over 800,000 numbers. Way too much data to handle. We need to zoom out, keep the important signals, throw away the noise. Enter maxpool. Maxpool 2D looks at small patches, usually 2 by 2, and keeps only the maximum value from each patch. If there's a strong edge signal anywhere in that 2 by 2 area, the max preserves it. The exact pixel location doesn't matter, just that something interesting exists there. After maxpool 2D with kernel 2, a 224 by 2024 feature map becomes 112 by 112. Half the height, half the width, 1/4 the pixels. but the important features survive. We do this multiple times. 224 becomes 112, becomes 5d6, becomes 28, becomes 14, becomes 7. Shrinking, shrinking, but the meaning stays. This shrinking gives us something powerful: translation invariance. A cat's ear on the left or the right of the photo doesn't matter. By the time it's pooled down to 7 by 7, the network knows there's an ear somewhere without caring exactly where. It sees the what, not the where. After all the convolutions and pooling, we have a cube of features. Let's say 512 channels, each 7 by 7. That's 512 times 7 times 7 equals 25,088 numbers. This cube is a compressed summary of the entire image. All the cats and dogs and cars distilled into 25,000 features. We can't feed a 3D cube into a classifier. We need to flatten it into a 1D vector, a single long list of numbers. In code, x.view, parentheses, -1, 512 times 7 times 7. Or just x.flatten parentheses 1. Now we have a vector of 25,088 numbers. Now we feed this vector into a linear layer. nn.linear, parentheses, 25088, 1000. Every single input connects to every single output. 1,000 outputs because ImageNet, the famous dataset, has 1,000 categories: golden retriever, tabby cat, coffee mug, volcano, ambulance. The linear layer outputs raw scores called logits. They can be any number: positive, negative, huge. Softmax converts them into probabilities between 0 and 1 that sum to exactly 100%. Now we can read golden retriever 92%, Labrador 5%, beagle 2%. The highest probability wins. So the full pipeline is: image goes into cond, then relu, then pool, then more cond, more relu, more pool. Repeat this a few times, then flatten, then linear, then softmax, then prediction. That's it. That's a convolutional neural network. Every image classifier on Earth follows this exact pattern. During training, we compare predictions to the correct label using cross-entropy loss. If the model confidently said cat, but the image is actually a dog, the loss is huge. The model was surprised. Low surprise means low loss. We want to minimize that surprise. Backpropagation flows through everything, including the cond filters. Remember, those little 3x3 kernels have learnable weights. Gradient descent adjusts them over time. The edge detector gets better at detecting edges. The fur detector gets better at detecting fur. The network tunes itself. After seeing millions of images, something magical happens. Early layers learn to detect simple edges: horizontal, vertical, diagonal. Middle layers combine edges into textures: fur patterns, scale patterns. Deep layers recognize high-level concepts: faces, wheels, written text. The network builds a hierarchy of understanding, from simple to complex. Let's recap everything. Images are just grids of numbers, RGB values. Convolutions slide tiny filters to find local patterns like edges. Pooling zooms out and keeps the strongest signals. After many layers, we flatten everything into a vector. Linear layers vote on categories. Softmax picks the winner. That's computer vision. In the next chapter, we'll build a complete CNN from scratch and train it on real images. You'll literally watch the filters evolve from random noise into actual edge detectors. It's the coolest thing in deep learning. Subscribe so you don't miss it. You built a brain. Part 1 complete. Next up, computer vision and CNNs. Teaching our AI to see, recognize, and understand the world. Subscribe for Part 2.